So we'll be using various techniques that we've discussed earlier to evaluate some integrals and see how that helps us. The first example is integral of tangent cube over cosine cubed. Well, this looks like it is scary somehow. You may try a u sub. U sub may help, it may not. But then recall that we can rewrite this to be the integral of tangent cube x secant cube x dx. And now the integral is of the form tangent to the power of m secant to the power of n, where these powers are odd. So we can keep one tangent and one secant and apply the thing we learned in section 7.3. So doing that, I'm going to keep one tangent, so I'll have tangent squared, keep one secant, so I have secant squared, then I have tan theta or x sec x dx. And why are we keeping one? Because we want to write everything in terms of secant and then make a u sub. So my tangent squared is the same thing as secant squared minus 1 multiplied by secant squared. Then we have tan x sec x, which I can write as sec s tan x, doesn't change anything. So I'll let my u to be equal to secant of x. This means that my du is equal to tan x sec x dx. So my integral that I had before will now be equal to integral of u squared minus 1 times u squared du. This whole thing here is du, which I can write as u to the power of 4 minus u squared all into the u. And what's my u? This integral becomes u to the power of 5 over 5 minus u to the power of 3 over 3 plus the constant c. And then take everything back to x. That would be secant 5 all over 5 minus this should be secant cubed over 3 plus c, and that'll be all. Let's look at another example. Now this doesn't look pretty like anything we've done before. So what do? Well, we see that if we have a radical involving linear factor, usually we can make a u substitution with the radical. So let's make a u substitution, u equal to square root of x. This means that my du is equal to 1/2 or 1 over 2 square root of x dx, which is equal to 1 over 2u du or dx, so that my 2 du is equal to, or 2u du is equal to dx. And then I can now make the substitution. My integral becomes integral of eu dot dx is u du. Now, how do I do this? Well, I can integrate by parts. Integrating by parts, I'm gonna get, letting this to be my u and this be my dv, I'm gonna get u eu minus integral of, if I differentiate this I get 1, and this integral e of u du minus that. However, I think I have 2u here, so I'm gonna have 2 here, 2 here. So this would be 2 into u e of u plus e of u, or minus, please, plus the constant c. Well, what's my u? Go back to my u. This is going to be 2 square root of x exponential square root of x minus exponential square root of x, then plus c. So my integral here becomes this. I know this because I know whenever I have a radical sign that contains a linear function, I can say that this is equal to, make a u substitution with u is equal to this. Let's look at another example. Imagine we are asked to simplify this expression. How do we simplify or evaluate this integral? Well, the fraction is improper, so we decompose into partial fraction and then integrate. So the strategy is to decompose into partial fraction and integrate. I'm not going to do this. No. This is improper. Okay. This is improper. The degree of the numerator is bigger than this. So we have the strategy is to divide first, then decompose into partial fraction and integrate. So this is what you do. Number one, here is number one thing to do. Number two is to decompose into partial fraction, and number three is to integrate whatever you have. These three steps, I believe you can carry it out. They are really very easy and straightforward. I'm just interested about the strategy to employ. If there is maybe a better or any manipulation we had to do, I could have done that, but this should be straight up something that you can handle. Okay, yeah, so this looks a little bit weird, but it shouldn't be. If you look at this, I can actually see an obvious substitution that I can make. The obvious substitution here is to let u to be equal to ln of x. This means that my du is equal to 1 over x dx. Do we have 1 over x dx? Yes. My integral, which is 1 over x ln of this dx, becomes integral of 1 over square root of u du. This will be integral of u raised power negative 1/2 du, which will be u raised power 1/2 over 1/2 plus c. That's going to be 2u raised power 1/2 plus c, which is 2 ln of x plus a constant c, and that will be all. The substitution here is very obvious and it's just for you to spot it. So the strategy here is to spot the obvious substitution and then integrate. Let's look at one more example. Now, if you look at this, it doesn't really look very cool. It doesn't look too good, but you could say, okay, since we have a radical sign, maybe we could make a u substitution here. If we let u to be equal to this 1 minus x over 1 plus x. Now you notice that my du is going to be a very complicated function of x, which I may not be interested in. So probably I may think it's possible there is another simpler method to do this. It's possible there may be an easier method. Maybe we should try some ingenuity, substitution, whatever. I know that I can write 1 over x over this, x to be equal to multiply top and bottom by something I can, okay, something I may want to write this way: 1 minus x over 1 plus x divided by 1 minus x. So the top will give me 1 minus x squared all over 1 minus x squared. So this would be equal to, that actually takes away the square root above. So I have 1 minus x above, and below is 1 minus x squared. That's, I got this by difference of two squares. So my integral becomes the integral of 1 minus x divided by 1 minus x squared dx, which I can write as integral of square root of 1 minus x squared dx minus integral of x over this x squared dx. And believe me, at this point you can integrate this. Recall that this would be, if you integrate this, you get inverse sine of x. And you can integrate this other one by making a u substitution. If you make a u substitution to integrate, you get plus this minus here. And when you make a u substitution, this minus is going to make this plus, and we have 1 minus x squared plus a constant c, and this will be all for this. So in all, you just kind of try to apply the method you use and follow the strategy we talked about in the previous video that was discussed in full details. We are supposed to have talked about section 7.6, which is integration using tables and computer algebra system. Because that is not necessary in this exam, and because of the nature of the class, like, I wouldn't require you to start pulling up tables of integrals online. If there are some integrals I think you should know, I will put it in your formula sheet. And a computer algebra system is just telling you to, like, go online or maybe use some apps to do all your integrals and write the answer. I don't want to do that. So I will skip section 7.6. Skip section 7.6. It's not necessary. If you maybe are in the engineering department, or maybe you're in math department, math major, you would probably come across a course where you will need this. But for now, I don't think you need it, and don't be tempted to use any of the either a computer algebra system or pulling out some integral tables online. So this will be the end of this video, and the next video will be talking about section 7.7 of chapter 7.